Alright, so this is for 7.3. Again, talk about least squares, approximations. Gonna work through that. So I want to show you how it's done first, okay? And we'll kind of go from there. So we're gonna do a linear approximation this time. I've got some x values. Here's the y's that go with them. I'm just making this data up in case you're wondering. Okay, just some data I made up. Okay, doesn't mean anything. Don't even know what it means. Don't even care. So what you've got, of course, if you make a scatter plot, it's going to look something like this. And the idea is you want to fit a line to it, and you want it to be the best line possible. So a couple of things. First of all, here's your regression from here to here. This is a difference, you see, of the actual value minus the predicted value. This is this distance would be actual minus predicted, and you'd end up this one would be overestimating the actual. This would be underestimating because it's above the line. And so that difference there, you want the sum of these squared differences to be a minimum. Okay, that's what least squares regression means. And I'll show you a little bit about that in Excel in a few minutes. But now here's how it works. Because in the past you had, you have two unknowns. It's all you got an a and a b. If you're doing y equals linear regression, y equals x plus b, right? That's what you need to find. Okay, or a lot of books will write it this way instead: beta naught plus beta 1 x. And that's how they're writing. That's how we're going to actually solve for it. Although it can totally be done the other way around too. Okay. So first and foremost of all, what you have for x's is you have a matrix that looks like this. Where this column is all about the constants. Call this our x matrix, times our coefficient matrix, which is beta naught plus beta 1, like that, and then it will equal our y matrix. Now remember, this is a 10 by 2. This is a 2 by 1. So what we'll end up with is a 10 by 1, which is what we have because we've got a bunch of y's. These are our y's over here. There's 10 of them. Yes? Now to do this, what I need to solve for is I need to solve for my beta matrix. This guy right here, I need to solve for it. Well, how am I going to do that? We need to get rid of x. How are you going to get rid of x? Ooh, I'll do the inverse. No, you won't, because the inverse does not exist, because it's not a square matrix. So first things first. Right now I clearly have this guy. I have x times beta is equal to y. I'm going to leave a little bit of room. So I'm going to hit it with x transpose. And when I do that to one side, of course, Mrs. So-and-so back in the day said I have to do it to both sides. And she was right. But that's not helpful. But now this is square, so it does have, or at least it should have, an inverse that exists. So I'm going to hit that with its inverse. And of course this all now becomes the identity times beta. Of course, if I do it to this side, I must also do it to this side. And this right here, when you multiply it out, will end up being, and it'll be obvious in a minute, it'll be a 2 by 1 matrix, where the top one is beta naught, and the bottom one is beta 1. So we're going to go ahead and run through this just for a good time, to see what you think about it. I think I'll do it by hand just for fun at first, because I can, I guess. So yeah, I guess let's quit screwing around and just do it. Where's my original data? My original data is up here. So 13, 16, 17, 20, 21, 26, 21, 25. Cool. Now notice it says to take the x transposes times the y's. I can do that. So this will become a long 2 by 10 times a 10 by 1 And what I'll end up with is a what? We'll end up with a 2x1 when I'm finished, right? So if I do this, really, if you think about it, the transpose is going to be the x's times the y's. So I'm going to have x's up here, x's times y's, and then I'm going to sum them up. So when I get down here in a minute, I'm going to have the sum of the x, y's is on my top row. Then I'm going to take a whole bunch of 1's, multiply it times my y's, and my bottom row is going to become the sum of the y's. Is everyone clear on that? Okay. Now, let's see what happens when you take x transpose times x. So if I take x transpose, which is a 2 by 10, times a 10 by 2, I'll end up with a 2 by 2, obviously. Okay? But what will this be? Well, this will be x's here, times the column of 1's will be the sum of the x's. Okay? And then second row, or top row, second column is going to be, what's going to be x's times x's is going to be the sum of the x squareds. Right? And then the bottom row is going to be the 1's times the 1's, it's going to be 1. And then it's going to be the 1's times the x's would be the sum of the x's again. Okay? Now think about that for a minute. That's pretty cool, but this is where it gets interesting. Because now I need to take the inverse of this guy. So when I take inverses, what happens? Okay, we flip and switch, right? So we flip and switch them. Oh, just a second, I gotta pause something here. Alright, I'm back. Sorry about that. Take care of something. So the sum of the x's and the sum of the x's switch places. That's cool. This becomes -1. This becomes negative x squared, right? And then what are we going to divide out by? We're going to divide out by the sum of the x's squared minus the sum of the x squareds. Right? Right. Awesome. So, let's see what this happens here. So I'm going to take this guy here and we're going to multiply it by the sum of the xy's and the sum of the y's, right? Because that's what we had on the other side so far. Okay? So when we do that, we're going to get, of course, this is a 2 by 2 times a 2 by 1. We're going to end up with the sum of the x's times the sum of the xy's minus the sum of the x squareds, sum of the xy's. No. What just happened? Oops, that's not right. So it's this times this plus, right? And of course that is divided by this. I did it backwards. And then on the bottom, you're gonna get negative like so. Now, that's all well and good. Jake, can we do this on our calculators, please? Yes, I'd love to. So what I'm going to do is pull up my Desmos. Not Desmos, I mean so this first guy here is what's called the design matrix. We've decided to go linear in our design. You see this kind of pain in the butt doing it this way? So what I'm going to do instead is I'm going to input it as the transpose, and I'm going to transpose it. So I'm just going to do There it is. Perfect. And then I'm going to store that sucker as a. Cool. And then I'm going to do the same thing with y, except that it's, again, I'm just going to input it in as if it was a long row vector instead of a column vector. Just because it's easier to input. Okay, so what I'm going to do is, again, I'm going to take, so A transpose, darn it, A trans, what are you doing? Why aren't you clicking? What is wrong with you, you piece of garbage? A. Good night. Okay, there it is. Okay. Now I'm going to take that answer, whatever it happens to be, and I'm going to multiply out in front of it by a trans. Darn you, all the thunder. Shh. Oh, what do you see what I did wrong there? Right there. Needs to be an inverse. Good night, nurse in a bucket. Alright, now if you hit diamond enter. Bam, there. I said diamond enter. Judas Priest. Remember those numbers, friends. Okay, now I'm going to bring up Excel. I think that's just helpful to see it like in a way that you've probably normally seen these guys over the years. A little Excel. My word, I'm having a day. Okay. I'm sure most of you are familiar with this. So if a fella could, of course, if he wanted to, and I think you always should, this is my personal belief, you should always make a scatter plot whenever you're doing statistics. Hey, look, it's linear. Who saw that coming? Ish. Right click, and we can go add a trend line. Okay, the default is linear. Display equation on chart. Display r squared on chart. Now, we're not really into the r squared part right now, but look at that, 2.0182, 11.22. Somewhere I had those answers a minute ago, I think. Was it on my calculator? Oh, yeah! There it is, baby. It's kind of neat to know. Now, in Excel, there's a kind of a cool thing about Excel that I like to do. My buddy taught me this a couple years ago. And so, what he did, and I thought it was kind of the neatest thing I've ever seen in my life, probably. You put A, well, let's just put A over here. I'll do B0 for my beta naught, and my beta 1. Cool. And then I'll just put in down here 3 and 10. If I didn't screw this up, well, whatever, it's not important. Now, if I do this, I go equals this guy. So lock it in times, that is, if you will, oh, that's my beta naught. So beta naught plus beta 1 times my x's. Hit enter, and there you get this data. Okay, and then I take, oh mama, what did I just do? That's weird. Oh. What? Oh, I see my problem. It's not beta 11. It's not 11, you clown. For God's sakes, it's embarrassing. Alright, here we go. So, I meant to do... There we go. I bet it'll work now, stupid. Alright, there we go. So then equals, what I want is the difference in the actual and the predicted value. So what I'd like to see is equals the sum of these squared differences. I'd like that sum to be a minimum. Now you can actually do calculus for this, but I think it's kind of neat just because it's not part of what the curriculum is asking me to do right now. But I think it's kind of just neat to bring this in. I want this thing here to be a minimum value. It says 196 needs to be a minimum. I'm going to do that by changing these two cells here. And I hit OK and cross my fingers. Oh, mama! That's exciting. You see what I did there? So what it did was, it took and changed these guys so that it would change these numbers, which changed these squared differences, and the sum of these squares here is a minimum when beta naught is this and beta 1 is that. Okay, that's what least squares regression always means to us. Now, to this juncture, I'd like to show you something else. When I was a kid, for regression, least squares regression formulas. This is so gross. Pretty sure it's this one. It's not what I want. Here, let's see if I can put the sum of the squares. I'll put this in sum of the x's. Oh yeah, by hand. There you go, by hand. There we go. Oh, here it is. Here it is. Yep. There it is, friends. Bam! Bam! So if you calculate the slope, it's the sum of the x, y's. Sum of the x, sum of the y's. We did that. And then if you'll notice that ours, what I had versus that is very similar. Oh, mercy. So let's bring theirs up. Okay. So the sum of the xy's times the sum of the x's. Well, what is the sum of the x's? The sum of the x's is how many x's there were, so that's actually an n right there. But that should come out to be, because it was actually the sum of 1. So sum of the x's, it should be an n right there. Wait, that's not the right one, it's this one down here. Yes, this is my slope one down here, right? Yeah, this is my slope one. Notice how they factored the negative out of these and had them backwards. You see that? See they have them backwards there, or flipped around. They flipped the bottom one around. They multiplied through by the negative top and bottom. So I would flip it around, and then I dropped a factor of n somewhere because there should be an n here and an n here, and that's because of the sum of the ones. The same thing is true on this one up here. Yeah, this can be simplified a little bit more, but that's the same idea. Okay, that's where that stuff come from. And I remember back in the day going, and it didn't make any sense to me. Okay, now I'm not going to hold you responsible for that, but that's where that stuff comes from. That part of it, that's something I want to think about. And then number two, I would like to go back and look at this thing right here a little bit more. Okay, I'd like to look at that thing there a little bit more again. So if you'll notice that I have the sum of the x's divided by this thing, the sum of the x squareds divided by this thing, and so on and so on and so on. Okay. Right. And so I'd like to talk a little bit about the covariance matrix, but we'll do that, I guess, in a little bit. So what if I had another one where I wanted to do not a linear regression, but what I want to do a quadratic regression. So someone might very well say, I want to do quadratic regression, J, and so my data points are 1, 1.2, 2, 4.7, 3, 10, 4, 15, 6, 37, and so forth and so on and so on. Okay? So then my equation would go down like this. Oh well. It would go 1, x squared, because it's constant, linear, and then quadratic, because what you're in essence searching for is a plus bx plus cx squared. That's normally how your book write it. They'll write it like this. Like that. So what you'll be doing then is you're going to have 1, 1, 1, 1, 2, 1, 2, 4, 1, 3, 9, 1, 4, 16, 1, 6, 36. That would be your new matrix right there. Of course, you'd have 3 unknowns this time, beta naught, beta 1, beta 2, and of course equals to a string of y's. Right? The equation, however, for your beta naughts is always the same, friends. For your beta matrix, to find it is always going to be every single time. Every single time. I cannot stress that enough. So your design matrix determines how you're going to set it up. But once you set up your A, that just determines that. That's it. That's all you need to know. Then it's simply going to be always this. Maybe I should use. Darn it! I've been calling this an A matrix. It is an A matrix, but you can call it an X if it makes you happier. Because I like the X's because it reminds me that it's the X's that are in that guy. Okay? Anywho, let's try this. Again, I'm going to do it in columns, but I'll do it as a transpose. So I'm going to do 1, 4, 9, 16, 36. Oh, wait. Oh, I know I did wrong. So 1, 1, 1, 1. There's my matrix. Would like to store that sucker as A. Cool. And then There's your constant, there's your linear term, there's your quadratic term. Okay? And do the same thing in Excel, of course. Excel will give it to me just like that, no problems. I'll do it this way. I'm just going to use another sheet though. Okay, there's my X's. My Y's are here. Ah, you hippie. Darn you! Piece of garbage. So, oh, no. Cool, there we go. Now, again, you make the scatter plot of it, you realize that right away it's not linear. Pretty darn quadratic-y. So what I do, oh, well, I can do it that way too. Let's go back to that, sorry. Insert a graph, scatter plot. So let's go to the trend line. So you can right click on a point. You can add a trend line. This time it's a polynomial. Second order polynomial. Display equation. There's your r squared. And if you look, that is exactly, I think, what we had over here. Or no, it wasn't on this deal, it was on calculator. Okay, gotta fix that just a minute. Something's going screwy there. Of course, you already saw it. I made a little boo-boo on when I entered the data initially. So that does impact things a little bit. Oh, now it's going to be pissed off. Stop it. Okay, something's still a little wrong. Holy crap, I thought I was losing my marbles for a minute. So I was getting the wrong answer. Then I found that I had put in a 1 instead of a 10 in my B matrix. I thought I changed it. I never changed it, apparently. That's the correct answer. That's what Excel gets. That's what we should get. Everybody's happy. Holy mackerel. Notice, however, that I put them in backwards last time. It doesn't matter. The way I put it in, it just flips it around. So instead of getting this, what I actually got last time was beta 1, beta not. It's not a big deal. Just be aware of that. Same thing on this one. I ended up, when I went back and was messing with it, I ended up getting beta 2, beta 1, beta. No, that is the traditional ax squared plus bx plus c routine. It doesn't make any difference. Just make sure that you're aware of what it is that you're getting when you're finished. I think that's what's always kind of nice is about a graphing calculator. A guy can always go and check himself real quick. Does that seem reasonable, logical, whatever? And so in the case of mine, I knew I was wrong because, you know, Excel's not going to mess it up. But I graphed them. You see the red one's terrible, but this one's actually really good. See that? Fits the data real well, and I can check my model. If I had like the 1.1 and the 1.08 backwards, which the only thing that would matter, if this 1.1 wasn't at 1.1, it was like 5, and I put that over the x squared, it'd make a huge difference, okay? If I flip-flopped them here, you wouldn't know much of a difference at all because 1.088 and 1.1 are basically the same. So, okay. one more thing, then I want to call this video good. There's not much to this stuff. Once you see the pattern once, it's so easy to do. Okay, last thing I want to talk about, and your book doesn't really go into detail on this at all, but I think it's kind of important from a statistical standpoint. I think it's kind of neat to see it. Often you'll hear about variance and covariance, and we've talked about variance. If you had a stats class at all, you've ever heard that. You've heard me mention variance quite a bit. It's the idea that, you know, how much change do you see from position to position to position. So for instance, do a nice easy one here. Okay, the variance of this guy would be, in essence, the average distance from the mean. The problem with that is that when you do that, you end up with, well, the mean is 3. So if you do 1 minus 3, you get negative 2. And if you do 2 minus 3, you get negative 1. And then if you add these up, what you'll end up with is a big fat 0, which is what it always happens to be, because that is by definition what the mean is. So that's not too swift. So what we do is we do the average squared distance from the mean. So when I square these, they become positive, of course, and they get bigger. And for no apparent reason other than I told you to, that's what we do. So 4 or 5 is 10. So you get 10. And then we take the average, so you're like, oh, divide by 5. Well, kind of. But okay, we'll leave it at that for now. We'll say, yeah, kind of. Okay? Now, that having been said, this is how much variation. In other words, it's about 2 is the variance, which is, if you will, the average squared distance from the mean. And of course, if you square root that, you get square root of 2, which is what we refer to as the standard deviation. And it's not perfect because this is the population sort of that we calculated, so it's kind of weird, but whatever. That's how it works. Now in matrix format, it's going to look a little different. Okay, so on our first one, we had column of 1, and then our second row was, what was our second row? Our second row was, oh, fiddle faddle. Oh, 13. What are you doing? And then, yeah, the numbers 1 to 10. Now, it turns out we can find what is referred to as the variance-covariance matrix. And we can do that. We can do that by finding the average of each of these columns. So if the average here is going to be 5.5. Of course, the average here is 1. Duh. So what we do is take a matrix of those averages, and you subtract those off. And what you do is you're creating a quote-unquote a centering matrix. Oh, so this ends up being 0. Well, 1, 1. 5.5, 5.5, 5.5. So what you end up with is this guy right here, which a lot of books refer to as X sub C. That is the centered matrix, because you centered it at its mean. Negative 4.5, negative 3.5. Right in the middle, you're going to get a negative 0.5 and a positive 0.5, because there wasn't a 5.5 in my data set, and of course positive 4.5 at the top end. And so what you do to find the variance-covariance matrix is you take X C transpose times X C. Now look at what that's doing to us. Okay. I'm going to die. If you take the transpose of this thing and flip it around, you're going to get zeros times zeros. You're going to get zeros. That's obvious. Now, you're going to take, and you do that, you're going to get a row of these differences, which are, again, are X minus X bar, like that. And then you're going to have a bunch of these Xi's, and then times another bunch of those. What you're going to get is you're going to get the sum squared, right? And then on the next one down, you get 0 times that again, which is what it is. And actually, this should have been right here. I'm sorry. This should have been a 0, and this should have been a 0 as well. And then, of course, we divide out by the number of them. In this case, divide out by 10. And there you have it. So what ends up happening in this variance covariance matrix, you're saying that there is no variance in a bunch of ones. In a bunch of ones, there is literally no change. There's no variation at all. That's why there's a 0 there. How much covariance is there between the ones and the column of ones and the column of the x's? Turns out there isn't any variance there either, and we'll talk about why that is a little bit more in a minute. Is there any variation within the x's? Yeah, you better believe there is. They're all over the map. Okay? And this thing right here is what we call the variation of x. The variation of x, or sigma squared. Okay? That is the real reason why we do take the differences and square them and divide by the number of them. Okay, so we're going to divide out by n because there were n data points here. Yes, they're in this case 10 data points. Okay, that's where that comes from. Now, same thing can be done on the next one, and I did it in Excel just to show you. So the ones, the mean is 1, obviously. The mean of this column here is 3.2, hence the 3.2. The mean of this column is 13.2. Cool. So I took this column minus this column. I got a group of zeros. I took this guy minus this guy. I got these guys. Took this one minus this one. I got that one. Okay? So then what I did was I said, all right, let's do this. So I did take this guy here, transpose it, and then I multiply it by itself. Now I did this as a function. So I'm gonna do it again just for a good time. What I did was I went. Now it's important you do it this way. You have to highlight. You know you're going to end up with a 3 by 3. So knowing that going in is important. So what you're going to do is I've got a 5 by 3. So I can take the transpose of that. So I'm going to do equals m mult of the transpose of this guy with himself. Divide by 5. Control, Shift, Enter. Boom. And this is my variance covariance matrix. What this means is the ones have no covariance with either the x's or the x squareds. Same thing means going down the same direction. Here, this means the x's have variation within themselves that's equal to 2.96. And the x squareds have a variation with themselves of 155.76. Remember, that is the squared differences. If you square rooted that, you would be more. It would be the square. It would be the square root of the average of the squared distances. Okay. Now this right here, what does this mean? This is the covariance of the x's. How do I know that? Because it's in the second column, second row, third column of the x's with the x squareds of these two columns. That same thing can be said here. It's very much a symmetric sort of situation. Okay. Now that is important for a couple of reasons. Okay, but important reason number one, when you're doing a design matrix, you really want to stay away from things that have any kind of covariance, unless, I guess, in the case of a quadratic model, that's not possible. But let's say you have a variety of things like this. So if you had someone's blood pressure, and so this is their so your blood pressure is a function of your stress at home and your stress at work. And number of days you fish. Okay, clearly I think one can see that if one is doing this, I think everyone's pretty clear that if you fish more often, you're probably going to have lower blood pressure because it's less stressful, and obviously stress at home and stress at work are going to be contributing to you. My model is going to look something like this. I'm going to have some constant, well, I'll call it beta naught, where that is my borderline, that's my baseline blood pressure. Okay, plus I'm going to have some stress at home. It's going to add maybe 3.4 points or something, maybe 17, whatever points to my stress level. Okay, or to my blood pressure rather. And the stress at work, similarly, and then my guess is, and I'm going to write it as plus, but I'm going to go ahead and go on a limb here and say that days spent fishing is going to have a negative effect on my blood pressure. Okay? That makes sense? So, in this situation, what you'd end up with is you want to know, is there any, there's never going to be any correlation, there's never going to be any variance of the constant with itself. That's just ridiculous. So, in your design matrix, you're going to have 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? Okay, that's for the constants, as many as I need. Okay? It's for the stresses at home. Again, this is on me personally, so maybe I have a 23, a 14, a this and that, and whatever. And that never happens, and this, and okay, great. And then my stress at work, now, so there's quite a bit of variation in the stresses at work, yes? From day to day, and at home too, as far as that goes. And then fishing, I wish I could fish more, but there it is. And so then that would be that. That would be my design matrix. And when I did the covariance matrix on this guy, I'll try to do the covariance on this thing, what I have to be aware of is to say that, well, what does that mean to me? Okay, so what I'm going to do is I'm going to find the average of each of these columns. Boom. Okay. Right? Oh, here's my blood pressures. One time I was thinking around waiting for something at Fred Meyer's, and I sat down to check my blood pressure. Thought I had a heart attack. It was it was like 200 or something, or it was something ridiculous, maybe 199 or something. But I had a heart attack just from reading the thing improperly or whatever it was. It freaked me out. You can get high blood pressure just from reading your high blood pressure, apparently, right? So same thing here. I'm going to grab these guys and drag them across. Oh, so that's not going to be good because you're an idiot. Oh, it's too much work to do things right. Why would I do anything right, Jay? What is it? What did you do, Jay? Oh, for God's sake. No, that's right. What is this? What? Oh, for the love of George. Alright, so that's what we need to get rid of. We need to get rid of these guys here, because they're no bueno. No bueno, senor. No bueno. No bueno. Alright, so let's see here. I got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yay. Of course, this one's going to be wrong too, because I'm an idiot. Cool. So down here, what I'm going to do is I'm going to go, I know I have a 7 by 4, so I'm going to end up with a 4 by 4 matrix when I'm done. So I'm going to say equals M mult the transpose of this matrix with this matrix Control Shift Enter. Nice. As you can see, the covariance of zeros with any of the x's this x, or this x is 0. This is the variation within my stress at home. Okay, oh, what did I forget to do? Darn it, hang on, just a minute, I forgot to do something. Divide by 7. Oh, shoot, you shut up. Yes, you can if you hit Control-Shift-Enter, there you go. This is the variation of my stress at home. This is the variation of my stress at, oh, shoot! Okay, let's try this again. So I'm going to try 4 by 4. I'm going to go equals m mult of the transpose of that guy there we go. Now, oh, he did it again, idiot. Divide by 7. There we go. So this is the variation within my stress at home, the variation of my stress at work, and this is my number of days I went fishing variance. Now, I don't go fishing very often, so there was not a whole lot of variation there. Now, this is the covariance of, this is the second thing over, so that would be my stress at home with fishing. This would be my correlation, my covariance of my stress at work with fishing. Notice that these are parallel, these match up and these match up. This is stress at home, stress at work, covariance. Okay, so we call our variance covariance matrix. Now, you've often heard about as well, well, is there a correlation at all? Okay, now correlation can be done this way as well in this matrix format, and it can be with the x's. But I don't really want to talk about that right now so much as I want to talk about the x's and the y's. So if I go back to my original function over here, here's my original x's and y's, yes? So it turns out you can figure out the correlation of those guys pretty easily as well. And so you would find the center of them, and then you can find it. But so correlation, though, has to do with just one more calculation step, which I'm going to pause and show you that in a second. All right, and then the last thing that people often refer to about when you're doing regression, we talk about correlation, and we want to know how these two variables are correlated with one another. And so you can actually find that in a matrix format. Okay, this guy here, of course, 100% correlated with himself, obviously. This guy, obviously, again, correlated with himself, exactly. And this guy correlated with himself, exactly. But this guy here, like, how is the second thing correlated with the third thing? Okay, I don't know, but yes, I do know, actually. It's this previous value, okay, divided by, this is important, the square root of the variances, products of them anyway, for the rows and columns that he is in. Okay, and as he's in the third column in the second row, so you're going to take this guy here and this guy here, boom, done. So that's 0.976. This guy here will also go right here, because, again, oh, fart. Because it is a perfectly wonderful, what's the word I'm looking for? It is a perfectly wonderful, I shouldn't have done that. No, that's wrong. Just try this again. Because it is a symmetric matrix, and we like symmetry. What are you doing? God, you're a moron. Did you right-click on it? Click Paste Special. Because it's too easy, I guess. Ooh. Values only, stupid. There you go, idiot. Now, if you're up here in this first column, we said that there's no covariance. What does that mean? That means that there means zero correlation as well. The only difference between this guy here, when we do a variance covariance matrix, on the diagonals in a correlation matrix is always going to be 1, because you have 100% correlation with yourself. Does that make sense? So that's kind of a neat way of looking at it. You're like, well, wait. So back when you were a kid and you first ever saw just X and Y correlation like this, can this work the same way? In fact, it can. It does. If you come over here, paste, here's a column of data. It's 2 columns of data. It's no big deal, whatever. X's and Y's. Nice. Okay, that's nice. So would I want to find the average of each of those columns? Of course I would. So equals average. Because I want to do what? I want to find a centering matrix. There we go. So then I'm just going to say equals this guy minus this guy, and I'm going to give it one of these. Yes. So then when I drag it down, it doesn't move, but when I drag it sideways, it does. Nice. Double check myself, see if that worked. Yes, awesome. So I'm going to have a 2 by 2 when I'm down here. 2 by 2 matrix equals M mult of the transpose of this guy, comma, this guy. You get that. Okay, oops, darn it. Divide by 10 rather, sorry. Control Shift Enter again, there they are. So this will be the variance of this first column. This will be the variance of the second column of data. Sweet. And then these will be your covariances. Okay. So if I wanted to find standard deviations, well, yeah, standard deviations, but if I want to find the correlation rather. We'll find the square root of these two guys. Boom, boom, boom. Okay. And then what I will do, and again, this is nice and easy. It's just obviously the x's are perfectly correlated with themselves, and the y's are perfectly correlated with themselves. And then so if you go here, you're like, well, what's the correlation? The correlation is this guy divided by the square root of this. You know, so this guy here times this guy here. What does that mean to me? It means that they're highly correlated and they have a positive slope. Okay, now if you go back to our original problem, over here, we found our, maybe we did, I swear I did it, but I mean I don't see it right now. Let's go find that graph again. And we did a linear fit, which is the default display, and display r squared. Okay, you see, well, oh wait, Jay, it's 0.898. I know it is, bro. Relax, I got you. So what is the square root of 0.898? What? 947? Nuh-uh. Totes my goats, friend. Somewhere. Where did I put it? That was on this page. Well, somewhere in this mess, I did that problem just a minute ago. Oh, right there, 0.947. Ching! I did it, yay! And the crowd goes wild. Alright, so in that section, you're not going to be doing the covariance and the correlation. I just add that in because I think it's important. I think it's something that a lot of times we get skipped over in low-level statistics. We tell you how to find correlation, or we tell you how to find, or we use correlation and we tell you how to find standard deviation, but we don't tell you exactly why we do it the way we do it. And I think that's a little annoying. And now you're big kids.